We're going on now to Chapter 7, Section 4, Permutations and Combinations. I think these are going to be fun, and of course you'll need a calculator because some of these get quite tedious. As we did some counting by multiplying and adding in the previous section, one of the things came up that sometimes we would multiply 3 times 2 times 1, and then sometimes 4 times 3 times 2 times 1, and sometimes this. And, you know, we would tediously put that into a calculator. This one we know is going to be 6. And here this is 12 times 2, that's 24. And this is 20 times 6, that'll be 120, but it does get a little challenging. Now, mathematicians have developed a little math procedure. When you have something like this, you're starting off with the number 3 and you're multiplying it by each of the natural numbers until you get to 1. And here you start with 4, multiply it by each of the natural numbers till you get to 1. 5, the same. So they've developed something that they call factorials. That for this particular calculation, you would write that as 3 factorial. For this one, you would say 4 factorial, and this one 5 factorial. Now, they do have a formula for it, for the number n. N factorial is such that you start with the first number, the first natural number, the highest one, take 1 away, and then take 2 away from that natural number until finally you get to the 1. And this is what is illustrated here. An interesting point is that 0 factorial happens to be 1, and 1 factorial is 1. You might think that this is 0, but no. A 0 factorial, by definition, is 1. So this sort of gives us our general formula. Now I'd like to point out something on the TI-83, turning it on. If you go to this button right here where it says Math, click on Math. If you then use the arrow to go over to the third column, you'll notice in the third column, number 4 is the factorial sign. So if you, for instance, said 5 and then do Math, use your buttons to go over to the third column and then down, or just hit in there number 4, it puts a factorial, the exclamation point, after the 5, and you hit enter, and it gives you your answer of 120. Again, I don't know how much you can see on this, but check your calculator, or if you're using the in-house calculator in Math Zone, you'll want to know where that particular button is, because it's a very useful tool. Now let's try some examples. Okay, these are pretty straightforward. In example A, it's 5 factorial. So, if you were to write it out, 5 times 4 times 3 times 2 times 1 equals 120. And if you put that in your calculator, 5 factorial, enter, you get 120. Now, what we want to show here is a little bit of strategy as well. For instance, here we have 7 factorial divided by 6 factorial. Well, what does that mean? Well, it's 7 times 6 times 5 times, and so forth. But 6 is 6 times 5, and then wait a minute, all of these would cancel out. So the strategy here is you write the 7, and then the number next to it is 6 factorial. But since our denominator is 6 factorial, these now cancel out, and you end up with 7. Now, if you wrote up all those numbers like this, they would just all cancel out as you go along. So here's a good case where we have 8 factorial, which is going to be 8 times 7 times 6, and then times 5 factorial. Why did I do that? Well, because in my denominator I have 5 factorial. So now these will cancel out, and I just multiply those. If you're doing it the old-fashioned way, if you put this divided by this in your calculator, you get this answer right away. And again, in many cases, they are encouraging you to use your calculator. But again, strategy. This one's interesting. 52 factorial divided by 5 factorial, 47 factorial. You might say, well, how do I do that? Well, you want to get a 47 factorial up in the top. So 52, 51, 50, 49, 48, 47 factorial. And then in your denominator, you're going to go 5 factorial, which is 5, 4, 3, 2, 1, times your 47 factorial. And now these cancel out. And if you multiply all of this by this, you get that as an answer. Again, the numbers get quite big. But once again, if you put this in your calculator, and I would suggest that when you do this part down here, you have your division sign. You put a parenthesis around that. So it'll be this divided by that, 5 factorial on your calculator, 47 factorial. It'll give you this answer right away. So, strategy. All right, moving on now, we're going to permutations. And I will read the definition from our textbook here. A permutation of a set of n distinct objects taken r at a time without repetition is an arrangement of r of the n objects in a specific order. So I kind of shortened it here in my notes. So a number of objects in a specific order without repetition. Now there's a couple of formulas here, and you're going to see how it ties in with factorials in just a moment. So in Theorem 1 they talk about the permutations of n objects. So for instance, if we had 7 objects and we're going to do those objects, 7 of them, how many possible combinations could you have? So it'll be 7, 7, and this would be then permutation of 7. So notice we have in our formula here n, the number, and n, the number. So if you see something like this where it's both n, you're starting with 7, you're taking it to 7 objects at a time, what are your possible permutations? It would be 7 factorial. Now as we continue, we get to Theorem 2, which is the number of permutations of N objects, but now they're taking at a number of times R. Let's say in our example here, we're going to have 4 objects. We're going to take them 2 at a time. How many permutations would you have? So for this, here's the special Theorem 2 permutation formula where there's an N and an R. So notice now, this is not another N as we see here, but it's an R. Now the formula for that is the N number, that is factorial, and it's going to be divided by, again, your number of items here, minus the rate at which they're used. So an example would be permutation 4, 2. So your number of items in your permutation is 4. That's 4 factorial, divided now by N, which is 4, and R, which is 2, minus 2. So 4 minus 2 is 2, and that is factorial. So you then say 4 factorial divided by 2 factorial, and keep in mind 4 was 4, 3, 2, 1. And, well, 4, 3, 2 factorial divided by 2 factorial. I did want that there, because these will then cancel out, as we were showing you before, and you end up with 4 times 3 is 12. Now again, if you put this in your calculator, either this way or that way, the answer is 12. So you want to practice using your calculator, because some of these get to be quite tedious as you go on. Okay, as we pick up, some key things about permutations I've added here is that where order is important, so it's a specified order without repetition. Order is important. When you're dealing with combinations, order is not important. Okay? And we'll get into the particular formulas. But one of the things you're asked as you do your quiz bees is to identify what do you have there? What are they asking you? Can you identify that they're asking you a permutation, or is it a combination? Or in some cases, and you'll see this in your quiz bee, is it neither? So these are examples I more or less copied right out of your textbook on page 365. There are 6 examples, and I'll put a few more up because I think it's worthwhile to think and discuss this a little bit. Now at a university, I put our own, 3 officers, a president, a vice president, and a secretary, are to be selected out of 10 candidates. Now, what is this? Well, you're going to select the president first, and then that eliminates that person, then a vice president, and then a secretary. So the order is important here. And this is a permutation. All right, in number 26, a school, whatever it is, a university, is to select 2 of her vice presidents. And then at a university they often have many vice presidents, 5 or 6 or more or whatever, to attend a ceremony. Well, she's going to select 2 out of a certain number. And is the order important here? Then the answer is no. So this is a combination. For 27, a student checks out 4 books from the library. And the library has a certain number of books, and they're checking out 4 of them. Is order important here? And the answer is no. So this is a combination. Now for number 28, a student bought 4 books, 1 for each of these family members: a father, a mother, a brother, a sister. So for something like this, is order important? And the answer is no. Or wait a minute, order is important. Father, mother, brother, sister. So order is important. And that's a permutation. Now in number 29, we have a father ordered ice cream, 3 different flavors for each of his 4 children. There was no order, and order is not important. And is it a permutation? Is it a combination? Well, you might think it's a combination, but notice they're not asking us for any of that. So for number 29, and again, this is a little challenging, this is neither. And then for number 30, a book club meets monthly at the home of one of its 10 members. It selects a host for each of its meetings of the next year. So again, when I was working on these in the quiz bee part, I found some of these a little iffy. And for this one, the book is saying that it's neither. So fortunately, we're not going to have too many of those. But I'll put up a few more, and you can maybe see things a little bit better. And also, we're going to look at some of the formulas that are involved here. Okay, a few more examples, again, out of not the text part, but the end of section questions that you can look up in your online textbook. And I've shortened them a little bit. And I'm pleased to say that generally we don't use the neither. So we're looking for either a permutation or a combination here in these. And I have put some formulas up. I believe we already had this one. If it's permutation, an order is significant, but the ends are the same. You have 12 out of 12, then it's just going to be 12 factorial. And then the other one is when you have a certain number, and out of that total number you are selecting, let's say 3 or 4, that's the rate. We went over that too just a little while ago. And that would be the formula. We'll get to use some of these. And then one that we haven't done yet, but we're going to be using here, is the combination. That's similar to the permutation formula, but we have this rate outside that we also divide by. So with that in mind, let's see if we can do some brainstorming and figure out first, is it a permutation or a combination? Now once again, we said in a permutation, order is important. In a combination, order is not important. So that should be what's on your mind as you go through this. So in a horse race, the first 3 places out of 10 horses in the race. So when you're talking about a horse race, is order important? Absolutely. So this is going to be a permutation. And what are the sub-numbers that you're going to put here? Well, how many horses are in the race? 10. So your first number is 10. And you're looking for the first 3 places. So it'll be 10, comma 3. All right, in the next example, we have a foot race. We want to find out the possibilities of the first 5 places out of, let's say, 50 runners. So again, when you have a race and placing in that race is important, order is important. So this is a permutation, and the number of individuals, 50, and the first 5 places will be a 5 there. Okay, and you're wondering how many different ways can 3 people be selected from 7? Let's say you want to form a subcommittee. In fact, that's what this is. I've shortened it. 7 to choose from, you want to select 3 people. Is order important? And that should be your first thought when you read this. Is order important? No. So it is not important, and you have a combination. And how many people on the committee or you're choosing from is 7, and you want to choose 3. So we have what I think here a good example of permutations and combinations. So let's see if we can apply these formulas then. So the one we're using, let's just number these here. 1, 2, 3. For this one, we're going to use the second formula. So this will equal 10 factorial over. Now we can do our subtraction right here. 10 minus 3 is 7. So you put that in your calculator, and I'll do that with you in a moment. All right, for our foot race, again, we're going to use formula 2. We have 50 for our number, and then we're going to subtract 5 from 50 to get 45. And you can put it in parentheses like I did, well, over there, or just like that. And for number 33, you have formula 3 that we're going to use. So we have 7 factorial. Now we need our 3 factorial out here. And then we're going to subtract 3 from 7 and get 4 factorial. And again, you need to have practice using our in-house computers, or actually I have a little Casio here that I was using this weekend, and turning it on. As I do the first one, I go 10, shift factorial is right there, divided by 7, shift factorial, and I get 720. So the answer to this one is 720. And these others are done in a similar way. When I put this into the calculator, I go 7 factorial divided by, I put a parenthesis, I then go 3 factorial times 4 factorial parenthesis, and then I get my answer. Okay, so again, we're out of order. We're going to go back to the textbook and give you some more material. I worked on the quiz bees and finished chapter 7 this weekend. Again, some of them are challenging, but take good notes, use the practice, show me how to do this, and I did that a couple of times. One of the many good things the textbook does is to give these illustrations that I thought was very appropriate here. And this is on page 360. So we're going back a little bit. And here they have 3 items, A, B, and C. And they want to see how many different permutations we can have with these 3 items, taken 2 at a time. So here we have the A, so we can pair it up with the B or the C. Then we have the B. We could pair that up with the A or the C. And the same for C. We could pair it up with the A or the B. Now, when order is significant, we can have here an A, B, and an AC. Here we can have a B, A, and a BC. And here we can have a CA and a CB. Now notice none of these are exactly the same. And how many did we get? Well, out of this we have 6. So for permutations, taking 2 of these at a time out of 3 items, you would write that permutations, 3 items taken 2 at a time, and then using formula 2 here, we get 3 factorial, which is our first number, and then we're going to subtract 2 from 3 and get 1. So 3 factorial is 6, divided by 1 is 6. So the formula matches up to what we have. Now, how about if order is not important and we have a combination? So now we're looking for those where order is not important, and they're the same thing in a sense. So can you see here we have an AB, and here we have a BA. If order is not important, this is just one unit that I've connected with this purple line. And then AC and CA. Order is not important, so they're the same. I'm connecting those with the green line. and then BC and CB. I'm connecting with the blue line. So how many combinations do we have where order is not important? Well, we're using this formula that we haven't really officially introduced, but we're using it. Our number of items to choose from is n, which is 3. And the items that we want to pick out are 2. So here we put 3 factorial. Our r is 2 from this formula. And then 3 minus 2 is 1. So we get then 3 factorial divided by 2 factorial times 1 factorial. And I don't know if you recall, 2 factorial is 2. 2 times 1 is 2. This is 6. 6 divided by 2. And again, put this in your calculator. Even though it's this one you could do mentally, the answer is 3. And that's what we have here. When order is not important, we have the purple of 2 that are the same except for the order. Green, 2 that are the same except for the order. And blue are the same except for the order. So there's a good little example. And then looking at the examples in the book, they're just using more of these. Now, as I did the quiz-mes, I did come across one that was rather a challenge, so I think I'll put that one up. I'm calling this next one an extra problem because I looked it up in the book. I didn't see any examples in the book, but I recall having one like this as a quiz-me. And again, let's just go over it for technique and strategy. They said that you had a permutation, 13(8), that was divided by a permutation, 8(3). So how do you do it? Well, you convert it. It's going to be formula 2 over here. You may not be able to see it, but your 13 factorial goes there. You subtract these 2, get a 5. So 5 factorial goes there. And then this is divided by 8 factorial. And the difference between these is 5. So 5 factorial. Now, this is a fraction divided by a fraction. And the technique to do this is you convert it from a division problem to a multiplication problem by taking this second item and flipping it. That is, take the reciprocal of this. So instead of the 8 being on the top now, it's on the bottom, and the 5 is on the top. So now you've gone from a division to a multiplication. That's key here. Now notice what can happen. We can cross multiply and cancel out these factorials. So what are we left with then? 13 factorial divided by 5 factorial. And when you put that in your calculator, you get 51,891,840. So you do get some big answers here. But I wanted to go over this technique that if you ever have something divided by something, you convert it to multiplication. Do any cross-canceling you can, and there's your answer. All right, we're moving along to card playing. Now, a standard deck of playing cards has 52 cards in it. I could remember when I was a young fella, and they said to me, do you want to play 52 pickup? Well, I had no idea what that was. And I wanted to play cards, and I said, sure. Well, they took the deck of 52 cards and threw them on the floor. And they said, go ahead, pick them up. You had to pick up the 52 cards. That's 52 card pickup anyway. Now in a deck of cards, there are 4 suits. Diamonds, clubs, spades, and one other. I got to remember what the other one was there. Hearts, there you go. Again, I don't play cards that often. But those are the 4 suits. Diamonds, hearts, clubs, and spades. And each of these suits contain 14 cards that start with a 2, 3, 4, 5, 6, 7, 8, 9, 10, then a jack, a queen, a king, and an ace. So I know a little bit about it. But anyway, you need to know a little bit about a deck of cards. At student unions, we used to play cards. They used to. I never did that much. Okay. Now, in example 6, it was sort of interesting. They're talking about how many 5-card hands, that is, the cards you're dealt, with 3 aces and 2 kings, if you had the 4 aces to choose from and the 4 kings to choose from, not the whole deck of 52. If they want you to use a whole deck of 52, they'll say in the quiz me or practice or a well shuffled, where they've mixed the cards up. But here you're just picking out of 4 aces and 4 kings, 3 aces and 2 kings. And order is not important. So you're using combinations. So it's to choose 3 aces out of the 4 that are there, and 2 kings out of the 4 that are there, and order is not important. So there's your aces, 3 out of 4, kings, 2 out of 4, and to get your total result, you need to multiply. This is a product of these. And this is sort of getting us ready for the next chapter, chapter 8, in which we do probability. So we need to know this to do that next chapter. So to set this up, we're using formula 3. So 4 factorial, r is 3. R minus 4 is going to be 1. So this later becomes 4 factorial, and 1 factorial is 1, so it's 3 factorial there. And this one is 4. We subtract r from 4, which gives us 2, which is 2 factorial times 2 factorial. And again, if you put that in your calculator, it works out. But 2 factorial, remember, is 2. This is 2. 2 times 2, this is going to become a 4 down here. And this becomes a 4 factorial is, let's see, 4, 12, 24. 4 divided into 24 gives you the 6. Here, this is just a 4, so your answer then is 24. So I tried to show you some of the traditional way of doing it, and then of course, become familiar with your calculator. That's going to be very useful in doing something like this. All right, we're going to continue with example 8 on page 364. And for example 8, there are 5 parts to it. All of them involve counting techniques where a company has 7 senior officers and 5 junior officers in their selection. And for part A, they're saying, what's the possible number of combinations, since order is not important, in selecting any 4 officers? So our group that we can select from are 7 and 5, which gives us a total of 12, and we want to select 4. Now in part B, they're saying they want to select 4 senior officers. So the number of selectees are just the senior officers. There are 7, so that is your number in the group, and you want to select 4 of them. So this combination will get you results. Now for part 3, they want to have 3 senior officers. Again, order's not important. And 1 junior officer in the select committee. So here it's going to be a product of the 3 of the seniors and 1 of the juniors. So again, there are 7 seniors. You want to select 3, so 7 comma 3 times there are 5 juniors. You want to select 1. Okay, now what we want to do is put these into formula 3. And I'll pause the tape, or you can pause it as you try to do that, and I'll do it here as well. Now, the next part is basically mechanical. We're using formula 3. So the 12 factorial, 4 factorial, and then 12 minus 4 factorial. 7 factorial, 4 factorial, and then 7 minus 4 factorial. And then here, 7 factorial, 3 factorial, 7 minus 3 factorial, 5 factorial, 1 factorial times 5 minus 1 factorial. And again, there's more to it, but by putting this carefully into your calculator, for this one, there's 495 possibilities, 35, and 175. I have a feeling the tape is getting long, and we want to wind it up. Okay, I'm going to wrap this up with example 8 because it's getting to be a little bit long. But again, this company has the 5 senior officers, 5 junior, total of 12. And then they're asking in letter D here that they want to have at least 2 seniors and at least 2 juniors. So this is a product of combinations. Senior officers, 7. We're going to select 2. Junior officers, there's 5. We're going to select 2. Multiply them together, and this ends up as 120. Now in letter E, this was sort of tricky, I thought. At least 2 senior officers have to be in the group. And an interesting thing, there's a couple of ways to do this. Actually, 3 distinct joint committees can be formed. So we have to have at least 2 seniors. So in our first case, we're taking, and there's only 4 members of the committee, 7 out of 4. In fact, that was problem B that gave us 35. Now in the next case, instead of having the 4, you're going to choose all the senior officers. You're going to have 3 senior officers out of the 7, but now there's 1 to pick out of the junior officers. That's what is illustrated here. And then in the next case, you're going to pick 2 senior officers, and you'll need 2 junior officers, which happen to be what we have here in letter D. So this is a combination of B, C, and D, where we add this together, and then the final answer is 420. And again, you don't have many of these. Some of these get to be quite challenging. Well, we wish you good luck. Once you earn your masteries, you want to test on Chapter 7, and that's sort of due this 5th week. And I'll start to work on Chapter 8.